discrete versus continuous compounding. So before we dive into the frameworks, let's see if we can develop an understanding of what discrete and continuous is. With discrete, we're assuming no compounding. In other words, no interest on prior interest. Continuous is the exact opposite. With continuous, the compounding is non-stop. So what we want to do is we want to develop a framework that shows us the equality between continuous compounding and what its equivalent discrete rate will be. So this is the framework that we're going to use. E to the x is equal to 1 plus r. And the best way to demonstrate the difference between discrete and continuous compounding is with an example. So let's suppose that a $70,000 investment 12 years ago is now worth $230,000. So there it is. Initially, we invested $70,000. 12 years later, it's worth $230,000. So the first thing I like to do is calculate the dollar profit. So the ending value was $230, but $70,000 of that was my principal. So therefore, the difference is my profit, which works out to be $160,000. In part 1, I want to calculate what my holding period return was, but measured using discrete return. In other words, without compounding. So here it is. I made $160,000 on an initial investment of $70,000. So that works out to 2.29. And then we convert it to percent, which works out to 229%. So over the 12-year period, if you don't assume compounding, I made 229%. But now what I like to do is I like to find out the equivalent rate of return, but under the assumption of continuous compounding. In other words, how might this performance be presented? Remember, it's the same investment. It's just the return is going to be measured differently. So I like to see what return this 160,000 translates into if we assume continuous compounding. So here's our framework, right? And we just need to plug in the discrete rate. Now, when you're doing algebra, it's always a good idea to use the decimal format of return. So there it is, 2.29. And so therefore that e to the x is equal to 3.29. And then you just take the ln of both sides. And then what happens is the ln and the e cancel out. And then you just have to find out what the ln of 3.29 is. And then your calculator spits out 1.19, and then we convert into percent, which works out to 119%. So ladies and gentlemen, check it out. The same investment, the performance may be presented in two different formats. So if you assume no compounding, that performance translates to a return of 229%. But under the assumption of continuous compounding, that same performance would be reported as 119% compounded continuously. So do you see how for the same investment there's two formats in presenting the return? Now the next thing we like to do is we like to annualize our return because that's how we facilitate comparison. For example, this 229 and the 119, that tells you what the return was over the 12-year period because we calculated holding period return. But like I said, we want to sort of facilitate comparison with other investments with different holding periods. So the best way to do that is to annualize these returns. Well, once again, would you like to annualize under the assumption of no compounding or continuous compounding? Let's see what the difference would be. So if you want to find out what the annualized return is without any compounding, i.e. discrete, here's the framework that we would use. So future value is equal to present value 1 plus r to the t. And the reason I'm using this framework is because you could see it right here. This is my future value, this is my present value, and that's t. So now we just need to figure out what the annualized return would be going from 70 to 230. So there it is. Just plug in the values. That's your future value, that's your present value, and t is 12 periods. So when you do that, the implicit assumption is that the r is being annualized. In other words, 70,000 being compounded at the annual rate of return 12 times will tell you what your investment is worth at the end of 12 years. So then it's just really a matter of solving for r, and I show you the steps here. Again, we're trying to isolate R, and then finally, when you solve for R is equal to 0.1042, and then you convert into percent, so that works out to 10.42%. Now, how about if you wanted to present it in a continuously compounded format? In other words, what would the annual return have been if we're using continuous compounding? So I'm going to show you two approaches. In the first case, I'm going to use this framework. Now, where did this framework come from? Future value is equal to present value e to the x to the power of t. Well, you know what? It's really just a copycat of this, right? Except what I'm doing is, remember we said that e to the x is equal to 1 plus to the r, right? So all I'm going to do is where I see 1 plus r, I'm just going to substitute it with e to the x, and that's all I did. That's it. So let's just go ahead and plug in the values. So there's our future value, there's our present value, and we know that t is 12 periods. So when you do that, we're implicitly indicating that the x is an annualized return, which is why it's been compounded 12 times. And then, you know, you just do it step by step. So here's the next step, and then this would be the next step. And then once you have it down to here, you just take the logarithm of both sides, right? And then what happens is the ln and the e cancel out, and then you just have to find the ln of 1.1042, which works out to 0.0991, and then we convert that into percent, and that works out to 9.91% continuously compounding. The other approach we can use is just by annualizing the discrete rate. So, you know, there's our framework again. That's the equality between the continuous and the discrete rates of return. So since we already have the annualized discrete rate, we can just plug that in, and then we can get the annualized continuous rate. So there it is. So we just plug in the annualized discrete rate, and again, I show you the step by step, and then you know, the ln and the e cancel out. You just find the ln of that. Once again, you get an annualized continuously compounded rate of return of 9.91%. Same answer as that approach. Ladies and gentlemen, I showed you both approaches so that you can just use the approach that you're most comfortable with. Okay, so now let's go and summarize the exercise that we just did. And this is kind of really important because it shows you that for the same investment, there are so many ways to present return. Look at the dimensions. First, we can look at whether you want to calculate the return over the entire period, in other words, holding period return, or whether you want to express the performance in annual terms. What's the next dimension? The next dimension is whether you want to use discrete compounding or continuous compounding. So there are many, many ways to present return, and as an analyst, you need to be fluent in all these different formats. So let's summarize this performance. So suppose we're looking at holding period return. Well, so over the 12 years, if you assume no compounding, that results in 229%, but with continuous compounding, it's 119%. And over the holding period, the dollar return was 160,000. Well, you know what? This doesn't facilitate comparison because these are rates earned over 12 years. So in order to facilitate comparison, can you tell me what the performance was on an annualized basis? Sure. On a discrete basis, in other words, if you assume no compounding, the annual return would be 10.42, but with continuous compounding, it'd be 9.91. And of course, so since it's a 12-year period, I can calculate what the dollar return was over a 12-year period, but it would be very faulty for me to calculate the annual dollar return because we don't know what that was. We just know what the beginning value is and what the ending value is. Now note the following. First of all, notice that the continuously compounded rate is always less than the discrete. Whether you're looking at holding period return, you could see that. Oops, wrong way. or whether you're looking at annual rates, you could see that the discrete is greater than the continuously compounded. So why is that? Why is it that the continuously compounded rate is always less than the discrete? Well, here's the logic. Continuously compounded rate compounds. In other words, it does more. Therefore, you need a lower value to explain the same data set. I like to think of it this way. This here is doing more work because it's compounding more. So you need less of it to explain the same data set. And you could see that it is the same data set. And one analogy that I always use when I'm comparing continuously compounded with discrete is the following. The more potent the medicine, the lower the dosage that's required. So if you can understand this analogy, so if you have a really, really powerful medicine, the doctor would likely prescribe a lower dosage. And that's the way I view this. So CC is a more potent medicine because it's compounding continuously. So because it's more potent, you need less of it to actually explain the same return series.